So next we need to synthesize alcohols. Let's start by doing that with both substitution and addition reactions that hopefully you recall from Orgo 1. So with a substitution reaction, remember you can start with an alkyl halide so that X minus will come off. You can replace that with either a base being OH minus in an SN2 type of fashion, or we can go through an SM1 type of reaction with just water. Now, usually you're going to use that with a little bit of acid, but it should work in theory with just water as well. So that's how you do substitution reactions. Remember, we really kind of try to stick with SN2 types of reactions, but on paper you can also do the SM1 reactions. If we instead start with an addition reactant, so that would mean that we're starting, instead of an alkyl halide, we're starting with an alkene. We can either make an OH that is the Markovnikov product, or an OH where it's going to be on the most substituted carbon or the least substituted carbon based on whatever reactants we're using. So if we use dilute H2SO4, or you can see this sometimes is written in many different ways. We could see something like H2SO4 in water. So it could say H2SO4, H2O. It could say H plus, H2O. It could say H3O plus. We could put catalytic amounts of H2SO4. All of those are saying the same thing. So just pointing that out because that can be confusing as well. You're going to get the OH on the Markovnikov product. Be careful using the one up top. This H2SO4 can and often will lead to rearranged products. And that's the reason why we have the second set of conditions down here, which is using mercury. And so mercury OAC2 with water followed by NaBH4 is probably a more reliable way to do that, unless you know that you're not going to have any rearrangements. So that's how to get the Markovnikov product. Getting the anti-Markovnikov product, we use instead BH3 and THF, followed by H2O2, water, and OH minus. Again, it could say NaOH instead of OH minus. That's still the same thing. So that's how we prepare alcohols and amines that you've already seen. And just to make sure that we're on the same page as we keep going here, I want to bring some things up. So the first is that when we're talking about oxidation and reduction, as far as organic chemistry is concerned, it's way easier than looking at what we looked at for Gen Chem. In this case, if you have more bonds between carbon and oxygen, that would be an oxidation process. And in fewer bonds, that's going to be reduction. It's kind of that simple. So here's what I mean by that. If you start off with a primary alcohol, that would be oxidized if you end up then with the aldehyde. Further oxidation will lead you to a carboxylic acid. See how we have 3 bonds to oxygen that way? Good. Reducing means that you start with the carboxylic acid. A reduced version of that would be an aldehyde, and a reduced version of an aldehyde would be an alcohol. So we're going to start seeing reducing agents. You've seen some of the oxidizing agents, but the reducing agents, and this is something that I referred to in the last video, we start looking at something called a hydride. So metal hydrides are ways to stabilize H minus, and that's the reason why you have a counterion with them, okay? So like this NaBH4, or sodium borohydride, it's got Na plus, and then this BH4 together has a negative charge. Well, when this reacts, we're talking about one of these hydrogens and its electrons coming off so that it's behaving like it were that. But H minus by itself is just too much of a, it's too unstable by itself. It just won't exist it's not going to exist that way. Lithium aluminum hydride is stronger. So this is a stronger more reactive hydride. It can do things that the NABH4 cannot. And so there's lots of other types of reactions out there that we use specialized hydrides for, but these are two of the main guys. So again, with the lithium aluminum hydride, you could have one of these hydrogens here come off as that H minus, and you still have that Li plus. Okay, so let's look at it. When we are trying to undergo reduction of either aldehydes or ketones, we have to remember something. And I would say that you have to remember this with all carbonyl reactions. That C right here, that is a sp2 carbon. And so this entire molecule is flat. If you're adding something from one side or the other, you can end up with something that is chiral. So it's a pro-chiral carbon in some cases, not all, in some cases. And so you have to pay attention to that. You will get both forms of a chiral center when possible, at least in the vast majority of the cases that you will see. So here we start with a reaction that you're familiar with already. So we have a C-C double bond as well as a carbonyl. In the presence of palladium and carbon, you already know that that double bond is reduced, right? So we end up getting a alkane out of that. But the same thing also happens when we're dealing with a C double O bond. So you end up getting that alcohol there, okay? Now, NABH4 and LiALH4 will do the same thing, notably with practically identical types of mechanisms. So in the first example with NABH4, you end up with this OH. Guess what? Same thing happens with lithium aluminum hydride. You get both stereoisomers if that stereoisomer is available. So the mechanism is very similar. In this case with NABH4, these electrons move over here so that hydride attacks the carbon. You might ask why that happens. Well, remember, in a C double O bond, whatever those R groups are, it doesn't really matter. What we end up doing is we end up having a partial positive charge on that carbon and a partial negative up there on the oxygen. So anything that is going to be like a nucleophile of any sort, such as an H minus, will be attracted to that carbon. So that's what's happening. And then once we kick up the electrons here to that oxygen, the oxygen is negatively charged. It will come and seek a proton source, and it does that using methanol in this case. Other alcohols would work there just fine as far as I know. I would probably try to not use methanol if it was me, but that's me. I'm gonna try to use ethanol or something. And if I didn't state this clearly earlier, these work with both aldehydes and ketones. So again, with an aldehyde or ketone, lithium aluminum hydride will give you the OH there. Very similar mechanism. The hydrogen comes and attacks here, electrons go up. And then with lithium aluminum hydride, as I said, it's stronger. So if you can't have any type of hydrogen source with it when it actually is used by itself, there's reasons for that we can get into, but just letting you know, you cannot use that in water. So oftentimes you can add water. I've also seen different alcohols be used there in that second step. Sometimes we just say H3O plus. There's a lot of things that you could write in, at least on paper, that would be okay there. You need a proton source, okay, in order to get that to an OH at the end. Now, the cool thing about using hydrides is that when you're processing these with a double bond present, the double bond does not get affected. So you can use the two different types of reactions based on what you need for synthesis. So if you need an enol, you need to have that O there, fine. Then use one of these methods in order to get you where you need to for synthesis. Okay? Okay. So when it comes to esters and carboxylic acids, you can also use lithium aluminum hydride. You cannot use sodium borohydride. Why? Because lithium aluminum hydride is stronger. Now, interestingly enough, carboxylic acids go by a totally different mechanism, but the esters will follow a very similar mechanism to what we just saw there. So I'm not going to go over that mechanism right now, but yes, you'll end up with a primary alcohol there. So let's look at the mechanism for lithium aluminum hydride along with our ester. Here we see that the hydrogen, just as we saw before, comes in here and these electrons go up. Now here's the interesting part. Because you have a built-in leaving group, these electrons fall back down and this leaves. So it leaves as an O minus, and that's what happens. And then you have a aldehyde. So this mechanism continues. You do have to have excess, but again, it's going to still, you can't really stop this. So you need to have excess in there if you're dealing with an ester. So at this point, a hydrogen source of some sort will, serve as your hydrogen there at the end. A lot of times that's going to be written as H3O+, but again, hydrogen sources can come in more than one way. We do tend to use this H3O+, though, more in this case. Why? Because you just got rid of an O with a negative charge. So we've got to get things balanced out again. Okay. Now, the last thing I'd say is that we've got to be able to prepare diols. We named them in the last video. We need to be able to prep them as well. These are done in very similar methods that you've already seen. So again, you can have two ketones, or we could have aldehydes. In this case, I showed you ketones. Palladium and carbon. Oh, I didn't write the carbon, so palladium and carbon. And H2 will give you this. You can use sodium borohydride, you can use lithium aluminum hydride, that's fine. And then as a reminder, things that you should have seen already, if we take a double bond that's there, we can use OSO4 followed by NMO, or we can use KMNO4 to get diols that are syn addition, so going in the same direction, as well as its enantiomer, if that's applicable. Or we can use peroxy acids, so RCO3H, followed by acid to give you an anti-addition. And if you're wondering why those are syn versus anti, feel free to go back, check out the mechanism again, okay? Thank you very much. I hope that's helpful.